What we're going to do in this video is think about the core relationships that define much of mathematics: functions, equations, and inequalities. We'll see how they relate to one another through linear models, and we'll think about how to represent these ideas both algebraically and graphically. All right, let's think about this together. A function is really just a mathematical rule that assigns exactly one output to each input. Let's think about it as a machine where you drop in an x, the input or independent variable, and it spits out a y, the output or dependent variable. The collection of all possible inputs is our domain, and all possible outputs make up our range. In this lesson, we will see linear functions, which are degree 1 polynomials that produce a straight line on a graph because they have a constant rate of change, or slope. It is usually expressed in y equals mx plus b, where m is the slope, rate of change, where it is different from 0, and b is the intercept. For example, let's say our function is y equals 2x plus 3. This function means that for every value of x, you multiply it by 2 and then add 3 to get the corresponding value of y. For each value x, the function will have a value of y, as shown. The graph of the function will be as shown. The graph is upward sloping because m is positive. If m is negative, or negative 2 for instance, the graph would be downward sloping, as shown. If the intercept is positive and negative, we'll move the graph along y-axis, as shown. We will see how we sketch the graph of a linear function later on, but first we need to see how we can find a solution for an equation. Now, once you understand functions, transitioning to equations is very natural. While a function describes a general relationship, an equation asks us to determine the specific value, such as the roots, that make a mathematical statement true. For linear equations, we can solve them by using inverse operations, like adding the same quantity to both sides or dividing by a non-zero constant to isolate our variable. Let's see our previous example. 2x plus 3 equals 11. To solve for x, we use inverse operations. First, we use additive inverse, where we add both sides minus 3, and we find 2x equals 8. Then we divide both sides by 2, so that x will remain by itself. Then we find 4 for an answer. Therefore, our solution set will be the set containing 4. Let's see another example. Here is a bit complicated equation, but remember, even though the equation has multiple terms, the main thing we need to check is the degree of x, no matter how many times it is repeated in the equation. If all the variable has the power of 1, then it is linear. To solve the equation, first we distribute the common term in each, and then collect the like terms. When we do that, we'll have 3 over 2x minus x over 3 minus 5 over 6x equal to minus 5 over 2 plus 2 plus 2 plus 6. When we do the arithmetic addition and subtraction by finding LCM for each side, we'll find 45 over 2 for an answer. Therefore, the solution set will be a set containing 45 over 2, or 22.5. But what if we aren't looking for just one exact point? That leads us to inequalities, where we seek a range of values that satisfy a condition. When solving linear inequalities, the steps are almost identical to equations, except for one crucial rule. If you multiply or divide by a negative number, you must reverse the inequality sign. Let's see this inequality, for example. Negative 2x plus 3 is less than 11. Just like we solved for the equation, we subtract both side 3 and find negative 2x is less than 8. Then here, when we divide both sides with negative 2, the sign will change, so we find x is greater than negative 4. Most students miss this, and their solution set will be incorrect. Since we get x is greater than negative 4, then our solution will be x is a real number such that x is greater than negative 4. Or we can express it in an interval as such. We used open interval because negative 4 is not included in the solution. But if it was x greater or equal to 4, then we would have used a closed interval as such. Now that we've seen linear equations and inequalities, let's move our discussion to how to sketch the graph of a linear function, whether it's an equation or inequality. This should be fun because we can unify all these ideas visually. The graph of a linear equation function is always a straight line, whereas the graph of a linear inequality function will be the shaded area below or above the straight line. Let's see an example of linear equation function. Here, we have a linear function y equals 2x plus 3. The first step is to find the x and y intercept. For x-intercept, we make y equals 0 and solve for x. Here, we find 0 equals 2x plus 3. Then, when we subtract 3 from both sides, we get 2x equals negative 3. And divide 2 from both sides, we get x equals negative 3 over 2. Hence, our x-intercept will be the point negative 3 over 2, 0. When we solve for y-intercept, we make x equals 0 and solve for y. When we do that, we find y equals 3. Hence, we will find 0, 3 to be our y-intercept, meaning the graph crosses the y-axis at the point 0, 3. Then we plot each point on our Cartesian coordinate and draw a straight line between the 2 points while extending it in both directions as shown. Just like that, we plot the graph of the function y equals 2x plus 3. Let's see another example. Here, our equation says y equals negative 3 over 2x plus 6. Let's find the intercepts first. X-intercept will be the point 4, 0, determined as shown, and the y-intercept will be the point 0, 6, calculated as shown. Then we plot these points on our Cartesian plane and draw a straight line passing through these points, and the graph of our function becomes just like that. Notice our graph is downward sloping, and as we discussed earlier, this depends on the coefficient of x, which here is negative. On the previous graph, it was positive, therefore it is upward sloping. Now let's move to linear inequality function graphs. In graphing inequality function, we do the same steps we did on equation function and shade the area where the function is satisfied. In an inequality function, its solution is more of an interval than a specific points. We need the points we calculate, as we did on the equation function, to determine the cutting point for the interval we require. Let's see the above examples in an inequality form. The first one is y less than or equal to 2x plus 3. Note that finding intercepts and graphing the equation will all be done the same for graphing an inequality function as well. But here, since we did the graphing for the equation, we just proceed with the graph from the above example. Because the inequality is less than or equal to, then we shade the area below the graph. We can take any point from below to verify the area, whether it satisfies the function or not. Let's take the origin, for example, since it is found below the graph. When we substitute 0, 0 in the function, it will be 0 less than or equal to 2 times 0 plus 3, which results 0 less than or equal to 3, which is true. Therefore, the area below the graph indeed satisfies the function. Let's see the other equation as an inequality function. The function goes as y greater than negative 3 halves x plus 6. After evaluating for the intercepts and plotting the equation graph, now we will proceed with inequality graphing. The one thing we need to note here is, since the inequality is strictly greater than, then it means the points along the graph won't satisfy the function. We can take one of the intercepts for checking. Let's take 0, 6 for instance. When we substitute in the inequality function, we find 6 greater than 6 as shown, which is false. Therefore, the points along the graph won't satisfy the function. Hence, the graph will be in a hidden line. Finally, since the inequality is greater than, then we shade the area above the graph. You can check any point above the graph for validation as we did on the previous example. On a general note, if it is less than or equal to or greater than or equal to, then the graph will be a solid line, as we seen on the first example. And if it is strictly less than or greater than, then the graph will be in a hidden or dashed line, as shown on the second example. To wrap everything up, functions describe the rule, equations find the specific points, and inequalities identify the regions. And we're done. Hopefully that makes some sense and helps you see how these algebraic techniques and graphical representations reinforce one another. If you found this walkthrough helpful, hit that subscribe button to join us for more practice here at Rimetric Walkthrough. And thanks for watching, and see ya!